Okay, so as I started to do in the last video, when I talked about rationalizing the denominator or dividing radical expressions, we did examples where we saw square roots. So we had to create pairs or to the second power underneath the square root. Now we're going to talk about a cube root where the index is a 3. So not much is going to change. Obviously, something has to change, but there are a couple ways to approach this particular problem, and I'm going to show you because I could represent 4 as a 2 squared. Do I have to do that? No. Does it simplify it a little bit more? Yes. But the idea is if I'm looking for pairs, if I have a square root, right? I'm looking for an exponent of 2 on a base under a square root to match the index. Then if I have a cubed root and the index is a 3, then I'm looking for exponents of 3 or triples, if that makes sense. So that means that I could do one of two things. I can say I have 1 4 and I need 2 more 4s. That's one method. Or if I write 4 as 2 squared, then that means I have 2 2s and I need 1 more to make 3 of them. So I'm going to do it that way because it's just going to give me smaller numbers and make my life easier. I can only multiply a cube root by a cube root, which is what I want to do. I want to maintain the index. But I want a 2 here because I already have 2 of them. So I only need 1 of them left to create 3. I'm multiplying. 2 squared times 2 is going to give me 2 to the third. I'll show you the next step in a second. Let me talk about the x's because the variables follow the same idea. If I have 1x, right, this is an x to the first power, and I need 3 total, that means that I need 2 more to make a total of 3. I'm multiplying x to the first times an x squared. That's going to give me an x to the third, and I want 3 of them because I have a cubed root. So I'm multiplying the denominator here by this to create 3 2s and 3 x's, 2 to the third power and x to the third power. Whatever I do to the bottom, I have to do to the top. So I'm going to multiply the top by the same thing that I multiplied the denominator by. So I determine what to multiply by based on, the amount of each that I need. So I'll show this step. When I multiply these two, I'm going to have a cubed root. I'll simplify that after. But I have a 2 squared times a 2, which is going to give me a 2 to the third power, which I want this to be either equal to the index or a multiple of the index so that it simplifies, right? The goal is to, get rid of the radical sign on the bottom of the fraction. X times x squared is going to give me x to the third. So this is looking good, right? I have an exponent of 3 matching the index and an exponent of 3 here matching the index. So I'm where I want to be in the denominator to get rid of the radical sign. In the numerator, I have a 2 outside of a radical and all of this inside, 2 times the cubed root of 2x squared. I cannot multiply this 2 by this 2 because one of them is outside of the radical and one of them is inside. I can't simplify this radical because none of these exponents are greater than or equal to the index, so I can't do much with the top. The bottom, though, I'm going to simplify. I'm going to just rewrite the top. Cubed root. Now, the bottom, this is multiplication. Be very careful where you put the index. You want to make sure it's in the radical. You don't want it to look like an exponent, on the coefficient. Sometimes that happens. So just be careful where you put that index. Now, what did I say? This 3 will cancel with this 3 to simplify into a 2. And then this cancels with this to simplify into an x. So now the bottom is rationalized. There is no longer a radical sign in the denominator. Technically, I would be done. However, we have to simplify all the way, completely. And why do I say that this is not completely simplified? Well, if you look at the fact that there is a 2 outside of the radical in the numerator and a 2 outside of a radical in the denominator, and this is multiplication and this is multiplication, I am allowed to cancel the 2's. Anything in the numerator of a fraction that has something in common with the denominator can go away, as long as it's multiplication. If this was 2 plus, that would be different. So the 2's are gone and I'm left with the cubed root of 2x squared on top, and then the 2 cancel, so just x on the bottom. I could not cancel the x's because one of them, or 2 of them I should say, squared, x times x, is under the radical, and this one is not. So I can't cancel the x's, and therefore, this is my final simplified, rationalized, radical expression. I divided these, this is what I got. I rationalized, this is what I got. It's simplified, okay? Obviously, a lot of different terms. Let me do another one, because it doesn't always have to be a square root. It doesn't have to always be a cubed root. You can have a 4th root. You can have a 5th root, but the concept is always going to be the same. Let me say that I have, let's just, the 4th root of 4x squared over the 4th root of, this up, 3x to the 3rd y squared, whatever. I made it up, random, but that's okay. I want to divide these radical expressions. Now, I could technically simplify if I want now because of the 4th root and the 4th root, but let's just follow. Actually, let me get rid of this 4th root like this and just make it 4x squared, just to make it follow suit with what we've been doing. 4x squared over the 4th root of 3x to the 3rd times y squared. So I want to divide these expressions, one of which is radical in form, or I want to rationalize the denominator. So I'm going to multiply by a 4th root, because only a 4th root can be multiplied by a 4th root. Now, how many 3's do I need? Well, I have 1 here. I can't rewrite it. So I'm going to need 3 to the 3rd here, because I need a total of 4, and I have 1 here, so I'm going to need 3 more. Let's look at the x's. I have x to the 3rd. I want 4 of them, so I'm going to need another x, multiplication, right? I have 2 y's, y squared, y times y, and I want a total of 4 of them, so I'm going to need another y squared. I'm going to need 2 more y's to make it a y to the 4th. And whatever I multiply the bottom of a fraction by, I have to do the same to the numerator. So both the top and bottom get multiplied by this. Now, how did I choose this? I chose this based on the fact that I need to create exponents of 4's on each of these bases so that they cancel the radical sign in the denominator. So looking at the bottom, I'm going to have a 4th root, and 3 times 3 to the 3rd is going to give me 3 to the 4th, which is what I want. I want this to match this so that it will simplify. X to the 3rd times x is going to give me x to the 4th, which is good. I want this to match this so it will simplify. Y squared times y squared is y to the 4th, which is good. I want this to match this so it will simplify. I want to simplify that in a second. Let's work the top. 4x squared is outside of a radical sign, so it's going to stay outside. And I have a 4th root of 3 to the 3rd is 27. This can't simplify because this is not high enough, right? It has to be either equal or greater than. And x, y squared. I'm not going to leave it as 3 to the 3rd if I'm not going to simplify it. I want to actually write it as a 27. And this looks worse than it is. It's not that bad because I did, oops. I don't know where that line came from. Okay, I did 1 at a time. But I'm not done because I have to re-represent or represent the denominator without the radical sign because I'm rationalizing. But I did everything I need to so that it cancels because this exponent, I don't know why this happens to me. Okay. Okay, so I have everything I need because these exponents match the index. So this will cancel with this, leaving me with a 3 outside of the radical. Don't forget that once you do that cancelization, I'm not an English professor, right? But once you cancel that, the radical sign goes away. This cancels with this, I'm left with just an x, and then a y. So 3xy on the bottom, boom, beautiful, right? Much nicer than it looked. The top is what's kind of ugly because I have a 4x squared times the 4th root of 27xy squared. That's okay. That's how it looks sometimes. Rationalizing, is mostly the denominator. Sometimes you're asked to rationalize the numerator, but you guys are going to be rationalizing the denominator more. Maybe if you go into higher level math, you'll do the numerator, but right now we're focused on just the denominator. The concept is the same anyway. Now, I did what I needed to do. I have no more radical in the bottom, but I have to make sure that nothing simplifies. I can't cancel anything, right? I have to always represent my final answer in simplified form every time. So what I'm looking for is something to cancel in the numerator that has something in common with the denominator that is either both outside of a radical or both inside a radical. So looking at this, because this is multiplication, I'm allowed to cancel. 4 and 3 have nothing in common. Nothing's going to cancel there. But an x squared and an x have something in common. There's x times x on top, and there's an x on the bottom. So one of them is going to cancel. This is going to go, and this is going to go, leaving me with just one of them on top. There's no y here, so this is not going to cancel with anything. And then I can't cancel anything here because those are underneath a radical. I'm only canceling things that are outside the radical. So what's left? On top, I have a 4x times the 4th root of 27xy squared. Right, I have this 4 and this x. This is a 4th root. It is not an exponent on that x. Be careful. That 4 is in the index. That's why I said be very careful how you write it or where you write it. Be clean with your work. On the bottom, this x canceled, so I'm just left with 3y. I am not allowed to cancel anything here because this is under a radical and this is not. So these y's won't cancel. The 27 and the 3 will not, and therefore I'm done. This is my simplified version of that rationalized, of this rationalized. So, it's a beautiful thing, huh? It's not as bad as it, just as it looks. Obviously, if I look at this now, it looks like craziness. But if one step at a time, it's not that bad. Okay, so